ABC Calc, this is going to be day 77. Today we're talking about logistic models. And logistic models certainly have a connection to both exponential and logarithmic functions. And you might remember talking about logistic models in pre-calc honors next year. So we're going to be getting into some logistic modeling pretty shortly here. But of course, as you've become so accustomed to at this point, I want you to try just a few quick practice problems before I see you next. There are 3 derivatives I'm going to have you find that relate to everything that we now know with e to the x. So think carefully, because depending on where, where the base of e is located, that might affect the way you find the derivative for those first 3. And then we have one integral at the bottom as well. Think about what might make a good u substitution there, such that you can evaluate and figure out the value for that definite integral. So try those 4 before I see you next. I'm going to go on to the next page, and we're going to recall some slope fields. It's been a little while since we've looked at some slope fields. So remember that the slope field is a graphical representation. It's the solution to a specific differential equation. And slope fields can be very useful to us because there are times where we can't solve a differential equation algebraically. So the graphical perspective is really all we have to go based off of if we wanted to talk about a solution to a differential equation. So here's the solution to dy dx equals y. And what you can see is that this is going to be something that is, as you choose different coordinate points along the axes here, you're going to see that it's what I would call horizontally stacked, right? At any given value of y, the slope is always going to be the same independent of what x is. And that kind of makes sense, right? We've made tables of values before, and we've been able to kind of calculate these slopes and kind of go from there. And as our y values increase, so does the positive rate of that slope there. And similarly, on the negative side of things, as y gets more negative, the slope is going to get more steeply negative below the x-axis there. So algebraically, what do we have going on for dy dx equals y? Can we figure out what y equals? Well, similar to what we did the other day, we can call this a separable differential by kind of interchanging the sides here. I'm going to pull the y down here, and I'm going to multiply the dx to the other side. So we're going to group the dy over y together, and on the other side put the dx. And once you do that, to figure out the value and solve the differential equation, right? Figure out what is the equation y equals. We can now integrate both sides. And we know the integral of 1 over y dy is the ln absolute value of y. And on this side, the integral of dx is just x plus c. Now, we talked about this in the other example the other day when we did a process similar. Of course, we would technically have plus c on both sides, but you can move all the constants over and just kind of leave the plus c on the left there, or on the right, I should say. All right, so then from there, what am I going to do? I'm going to convert this to exponential form, start getting y alone. So the absolute value of y would equal e to the x plus c power. And as a reminder, e to the x plus c is really e to the x times e to the c. And the reason why it's nice to write it that way, of course, right, multiplying 2 things at the same base, we would add those exponents. We can now rewrite this as, e to the c is just a constant value. So we can write this as absolute value of y would equal some constant, I'll call it k, times e to the x. And as you're looking at this graph, yes, certainly the patterns for these slopes, if you were to draw in a specific solution, it's following that exponential pattern of some form of y equals e to the x. Now, we still have that absolute value to resolve. So if we separate and break up the absolute value into those 2 pieces, we would get plus or minus k e to the x. And that's why we get that same kind of matching negative e to the x graph as our solution below the x-axis. And I just think this is so cool, guys. So using some of the techniques that we've seen in the prior lessons and some of the new antiderivatives we know, we now have a really good way to come up with an algebraic representation of this graphical representation of that slope field for the differential dy dx equals y. So some good stuff. Now, like I was saying right at the start of slope fields here, sometimes we don't know the algebraic solution. So what I'll tell you right now is for this example, dy dx equals e to the negative x squared. This does not have an antiderivative, which is just so wild. It's crazy that certain things, certain expressions don't have antiderivatives. But I can kind of get an idea as to what the solution would look like to this differential equation by using that slope field program on the calculator. So as a reminder as to how you would do this on your calculator, you would go to y equals and type in e to the negative x squared. A good idea is to use Zoom Decimal. Zoom Decimal is typically a good window, so you're kind of shortening up the window over which you're going to see all these slopes. So Zoom Decimal will be Zoom 4. It's going to actually graph e to the negative x squared for us. This is a function that we've actually looked at quite a bit in other contexts. We've done some like area under this curve here and there, maybe even a little bit of volume too. But it's an interesting function because it is elusive in the fact that it does not have an antiderivative when it's the solution to this differential here. Okay, so I'm going to move that aside for a second, and now that we have that graph, let's go to the slope field program on the calculator. So if you remember how to get there, you got to go to your programs. We're going to choose option, whatever it is in your calculator. Mine was 6. So we're going to do slope fields, and it's going to ask you how many marks across and how many marks down. Because of the window that we're using and the rectangular nature of it, if we go 13 across and 9 down, that typically is decent, especially if you have Zoom Decimal selected. And we start getting something that looks like this. So without us making the table, again, the great thing about this calculator program is it generates a family of solutions that would represent the solution to that differential equation. So you get kind of this curve in here, right? So there are specific curves we can try and draw as the solution family, but it's tough to know what that actual family of curves would be representative of. So in terms of what you're going to draw down there, I kind of just tried to do my best. I'll show you what I drew, but here's what I have. Something that kind of models that general pattern. You probably don't even have to draw as many dashes as I do, but for certain differential equations, we can only represent it using the slope field program graphically. We don't have an algebraic way to determine the solution here. Okay. So that's just kind of bringing back a little bit of some old stuff, right, with slope fields and connecting it to the new information, which is what we know about logarithmic and exponential modeling with some calculus concepts here. So let's move on to logistic growth models. Maybe if you learned about logistic growth last year, you might have talked about like the spreading of a rumor is a good example of logistic growth. Because if you think about the way a rumor would spread over time, I'm going to kind of draw that for you down here. What happens is as time goes on, the population of people who know the rumor, well, it starts off probably with like very few people. Maybe it's like one person who started the rumor, right? And it's going to grow pretty rapidly. And you're going to reach a point at some point in time where the rate of growth is going to start to decrease. So this is still an increasing function, but it's increasing at a decreasing rate. And it eventually levels off, because if you think about the rumor spreading just within the confines of Fairport High School, we only have a certain population here. Now, granted, with social media these days, rumors can spread much more widely, depending on what's put out there. But if we just think about, prior to those social media days, spreading a rumor in a high school building, it's going to have to level off. So you'll notice that in the beginning of a logistic model, it looks pretty exponential. But then after the inflection point right here, it switches over to something that's pretty logarithmic. We get this kind of like dampening effect as far as that rate of growth. So when an exponential model for population or disease is reasonable only for a short period of time, logistic growth models make sense to model the situation. And here's kind of the general model that we're going to be using to answer the question below. So it says in the example, the spread of a disease in a school is given by the equation below, where T is the number of days after students are exposed to infected students. So we get the model P of T equals 100 over 1 plus e to the 3 minus t power. Estimate the number of students initially infected with the disease. So the initial infection is going to be when time equals 0. So if I say what's P of 0, it would be 100 over 1 plus e to the 3 minus 0 power, which is e cubed. So let's see what that is. Got to quit my slope field graph here. All right, fancy fraction, 100 over 1 plus e cubed is 4.742 ... Okay, so I would say approximately 5 students, right, at the start. All right, part B, what is the maximum number of students who will get the disease? So the maximum number of students can be calculated because, again, we have this kind of like upper limit. Okay, there's actually a horizontal asymptote up here that the graph would be approaching. So if you take the limit as time goes to infinity of your function 100 over 1 plus e to the 3 minus t, what's going to wind up happening is this t gets larger and larger and larger and larger. This is going to be e to some negative power, which is the same as 1 over e to that positive power. And you can imagine if you have 1 over e to some power, as that denominator grows and grows and grows and grows, this is going to approach 0. So we know that this goes to 0. So we wind up getting 100 over 1 plus 0, in other words, 100. And what you'll find very commonly is in logistic growth models, that number in the numerator represents the upper limit, the max population here. So we would expect that maybe the max number of students who can possibly get the disease would be 100. And then estimate the number of days it will take for almost everybody, just 99 students, to get infected. So if we want the population to be 99, this is just going to be something we type into the calculator quickly. Let's let y1 equal the function p of t. And then in y2, we'll have 99. Okay, so let's go ahead and type this in, see what we wind up getting. So for y equals, let's go ahead and type in 100 over 1 plus e to the 3 minus x power. In y2, we want 99. And because we have y2 equals 99, definitely we want to set the window appropriately here. We were just using Zoom decimal. So for x time in days, if you're not sure how long this is going to take, I think that's of course reasonable. But if we kind of make a guess at it at first, like let's say we guess 20 days and see if that's enough. If it's not enough, we could always extend that further, of course. And then for y-min to y-max, I'll go from, let's say, 0 to at least 99. I want to give myself a little bit of breathing room. I'll go up to 150 for y-max. You can choose whatever you want, but let's see if we get a model that looks pretty similar to what we expected to happen here. And because that max population limit is 100, you can see that once you get up to y equals 99, how it really flattens out there. Right? It's going to follow that horizontal really closely. And if I shorten even the window up a little bit to, let's say, an x max of 10, you'll see a logistic growth model that looks really close to what I sketched up here at the very beginning. Right? We have that exponential growth in the beginning, but at a certain point, it reaches an inflection point and starts to level off. Okay, so hopefully we can calculate an intersection here. Second trace intersect. Calculator's pretty smart. So hopefully if I go out, I think it's going to happen prior to 10 days, but let's see. Hit enter 3 times. It takes about 7.59-ish days. Okay. So sometimes during the 7th day is when this would happen, or by the 8th day. I guess there's a few different ways you can answer this. If it happens during day 7, we'll say by the time day 8 rolls around, that's when we would have 99 students infected. And then finally, the last piece of this, it says, when will the rate at which the flu spreads be a maximum? And what is this rate? Okay, we want to know when the rate will be at a max. So when is the rate, which in this case would be dp/dt, at a max? So you can do this in a few different ways, and I am going to do it graphically. We already have in y1 right now our function b of t. So graphically, so that I don't have to find the derivative and go from there, we can just do n derive of y1. And that's going to represent dp/dt. And we can calculate pretty easily then once we look at the graph when that's at a max. Okay, so we'll go ahead and do that in just a moment here. The other thing I guess you could do is you could look at the second derivative, right? So if you wanted to even go as far as y3 and be able to analyze the graph of the second derivative, you'd be looking for when does it change from positive to negative? Because when it changes from positive to negative, we know that the first derivative would be at a maximum. Okay, so if you wanted to go that far with it, you could. Probably not necessary here. If I go to y2, I'm going to do math 8 and derive. With respect to x, alpha trace y1 for all x equals x. The nice thing about, remember the calculator, is that you don't have to graph both at once. So to give the calculator maybe a little less thinking, I'm going to turn off the graph of y1. I really only want to look at the graph of y2 right now. Let's see. So that probably should be good. I mean, I don't know if I really need to adjust the window much, but I'll hit graph. I'll use the same last window that I have, and it's going to think about it for a little while, right, as it graphs the derivative for all values of x. But it's not taking mine too long. So it looks like the rate is at a max, okay, when that first derivative reaches its max value, which looks like it's right around 3 days. We'll calculate that in a moment once it's done graphing. And then remember, the y value on this graph is the rate. We're looking at the graph of the derivative. So looks like mine's done. Second trace, let's calculate the max here. So scroll over to the left. Scroll to the right. All right, the max happens after, go ahead and guess, 3.0000, yeah, just about exactly 3 days. And the rate is 24.9999, sounds like 25 to me. Okay, so we would say that when will the rate? The answer is that t is approximately, it's actually not even approximately, we'll just say equals. I'm pretty confident that 3.000 is 3 days later. And then what is the rate? The rate, dp dt, is 25 students per day. Okay. So especially if it's not something we're forced into doing algebraically, you know, bringing in the calculator for something like this, I think is a great idea. All right. Last but not least, there is one more example that we'll probably wind up doing actually tomorrow in class, but just to kind of give you a little bit more of an algebraic perspective as to what we're talking about with logistic growth models. It says, recall in exponential growth modeling, the rate of growth is proportional to the existing quantity. Okay, so when we talked about exponential growth models, we know dy dt, which is the rate of growth, is proportional to the existing quantity. So we said that some rate or constant of proportionality times the existing quantity y. Well, logistic growth models, we have one new piece that we have to add on. It says in logistic growth models, the rate is proportional to the existing quantity and the difference between the existing quantity and the upper limit L. So when we talk about logistic growth models, you'll see it's proportional not only to y, which is the existing quantity, but the difference between the upper limit and the existing quantity. So this is kind of the new piece that gets added on when we're talking about logistic growth models. And in integral form, if you, again, kind of separate this and write it as an integral, you get something that looks like this. So it's dy over y times, in general, L minus y, that upper limit minus y, and on the other side, k dt, okay? So I'll leave it there for now. This example we'll do together in class tomorrow. I'll give you some time to look at it, but it's bringing back all the things that we actually just learned about. Here's a slope field, and that slope field is going to be representative of a logistic model, the solution there, because notice how it follows this pattern of some quantity times a limit minus the quantity. So if you want to start taking a look at this just to get an idea before we look at it tomorrow in class, go ahead. But otherwise, I'll give you some time to work through this next time I see you. So that's it for logistic growth models today. Don't spread any rumors about me, but if they do, I know that it will eventually level off. So that's the good news. All right, have a good day. We'll see you later.